Hello everyone. So my name is Akash. I'm working as a research and development engineer in Bralus Design Inc. And my my research and areas of work are in semiconductor design, specifically like cache, DRAM, memory controllers, and microarchitecture design, and interconnect devices like AXI and NOC devices. So in this training session, we will follow this agenda. I will first explain the resources that available resources in the VisualSim, and I will show how to run a model in VisualSim, and then I will explain the key library components that are needed in any design, and then the simulators, the applications and types of simulators, and then following that I will explain the modeling methodologies that we use in VisualSim environment, and then I will show few demo models to show like how we model the design and how we interpret the results to make the design, like to optimize the design. Is this okay?
Yeah, that's great.
Okay. Okay, so let me open the VisualSim tool. Okay, I think is my screen like is the tool visible to you?
Sorry.
I think
yeah.
okay, let me reshare the screen.
Yeah. Now we only see your slide.
Okay. Yeah, okay. Is the tool visible now?
Yeah, we can. Yeah.
Okay.
We can see your pictures. Yeah, yeah.
Okay. So let me explain the resources first. Like in VisualSim, we in this the user interface, you can see the in the left side, you can see the Learn VisualSim tab, in which you can explore various resources to get started with VisualSim tool. In this, you can select this library documentation, which will open through a default browser. You can use this any browser, and you can explore the documentation for each library blocks. So in this, the first tab says the block documentation of VisualSim. In this, you can see the entire library, the documentation for the entire library devices. For example, if I select the traffic and the traffic block, it will give the documentation for the traffic block, and uh, you can utilize this to configure the traffic block in the VisualSim environment. Similarly, you can observe the documentation for every library components in this VisualSim. Also, this documentation explains the like what does this block does, and the parameter configuration, the explanation of each, and what kind of values you can use. And similarly, what is how many ports will be there, and what are the purpose of the ports. So similarly, like you can examine if we check, let's say an expression list. We commonly use expression list, so it will define what an expression list is, how we can use this, and we can also it sometimes in documentation we can refer some model or locations. So it will refer a particular model so that you can use that model to get some better understanding. So these are for the block documentation. Next thing is we can use the tutorials to get started. So we prefer to use the tutorials like in this following order. So let's say in getting started, if we select the part one, we can see the tutorials like how to use the VisualSim and design this particular let's say like a simple model with users traffic queues and the delay and text displays. So the user can utilize these resources to identify where these resources are, like from where this expression list can be obtained, and how to configure the each blocks, and how to analyze like what kind of results can be expected, and how to observe the results. So with these tutorials, user can get some better understanding of how to use the tool, and they can start their own design after this. So this will be better for the first user to utilize these getting started tutorials like we have in different sections. Like these are for general applications like traffic and system resources, and we have detailed one like for architecture exploration like AXA bus, processor design, and cyclic rate processors, and similarly for networking. So this will be beneficial for user to get started with visuals. And these are like a detailed information about the inbuilt library functions that we have in visuals. So in case once the user get familiar with the tool, they can use this documentation to understand what these regexes are, like what this inbuilt library function can do, how to utilize that, like how can I uh, use the proper value in the regex. So user can use this as a reference method to when they design the libraries using these regexes, they can utilize these resources to understand if they made any mistakes. So these resources will be useful once they get started and familiar with the tool.
Yeah.
Yeah.
This regular expression is only specific to VisualSim.
Yes, this is specific to VisualSim. Yeah.
Okay.
Okay. Is there any other doubt?
Nothing. Yeah.
Okay. Similarly, we have videos, tutorials, and other resources like installation guide, how to use the specific features in VisualSim. User can explore these things to understand uh, the features and the documentation for each blocks or each models and all. And along with that, we have other features called post processor and batch mode simulations. I think we will cover in later training sessions. But for learning a visual sim at the beginning stage, user can explore these things. And we have a lot of demo models that user can utilize when they first enter the, like when we get started with visual sim. They can use these two sections like they have library and application, which means it shows if we click this, they will show the demo models according to the library. They have demo models for traffic. If you click this, it will open specific sections. And let's say like I'm saying file import, it is opening a model that is a demo model for specific function like here in traffic. If I'm using a file reader, it is showing a specific demo model. So user can select the demo models using this option or application based like and it is according to the application like hardware based designs applications. We can select any particular model and they can yeah, it will provide a demo model for that, and they can run the simulation, observe the statistics. And there is also one another way, that is exploring through the internal array. By default, it will open the home directory, which is VACR demo. Which within that, user can use these directories to observe, select any model according to the application, and run any. Let me explain. For an example, let's open the methodology and okay. Let's say I'm selecting performance and I'm selecting cache and I'm using this processor top model. So it will provide a basic example. So these are the inbuilt line models that are available in VisualSim whenever this tool is installed. So user can select any model like that. So for example, let me open. Okay, this is an example of how the resources available in VisualSim. And next I will try to explain how to run the model in VisualSim. Is there any doubts so far?
Nothing. Yeah, please give your training.
Okay. So I have a model planned for explanation. So this is a simple model with ingress queue and egress queue, like a two channel. So for just for explaining how to run the model. So once it is open, you can select this green button, which says play, which is a run button. Once it is selected, we can see the model is simulating the environment, but also we can see the status of the execution, like whether it is completed or is there any issues with the model. Now it says execution finished, which means the model is run simulated completely without any issues. So you can observe the statistics and plots and specific information that we configured in this model. So this is the way, like once how we run the simulation. So yeah, so let me explain the library components first. Then we will come back to this plots and the statistics and all, and I will explain these models. Okay, so the main library components, there are key library components that will be used in VisualSim in any design. So these are like simulator. We have to, I will show you how to use this, like where to select this, obtain the library blocks and how to configure it. So these are the main like library blocks that we use. So one is simulator and another one is parameter. That is also like a top level parameter that we configure at the initialized time and it cannot be changed during the simulation. Variable list, which uses like we will select the variable, but it can be changed, dynamically changed by the execution based on our logic. And we have architecture setup block. Like for simple model, like with the traffic or expression list, like a simple logic, we might not need this, but for a complex logic, like when we use cache, buses, processors, so those times the architecture setup block is needed to observe the statistics from each block. So this architecture setup block will monitor the entire architecture that we design and observe the statistics from that. And similarly, power table. So whenever we wish to analyze the power of the design, we will we'll use this power table and configure the state values. Like we will provide detailed information for this for the power consumptions. So I will explain those in detail later. Let me open the tool and okay, let me open the same model again. So we can see the first one is the simulator. You can select the simulator from the library sections. We have a explorer to select the libraries. You have to select model setup and digital simulator. You can just click that and drag and drop it. So with this, you can like add the digital simulator to the model and configure it. So with respect to digital simulator, we have to configure the stop time or the simulation time. So which means how long the mod we are going to run the simulation. So in this one, we can say it is by default the stop time is configured as infinity. We have to select a meaningful value. So for example, in this one, we have configured to a parameter. So which is actually 1.0 e power minus 4. So for 0.1 millisecond, we are running the simulation. So user have to select the digital simulator and then modify this value like 1.0 e power minus 3. So other than the user can leave other functionality as default for the initialization time, for the initial time. So these are like these can be advanced. Once they get familiar with that, they can configure it as per their expectations. But for the initial stage, they can just select the stop time and configure it. So based on this value, the entire model will run only for this time. And other thing is the parameter. So we can drag and drop the same parameter from the model setup in this parameter section. We can see we have a lot of parameter here. So these define how we are configuring the model. For example, if I click in this view, we can see these parameters are configured as ingress size, threshold, output rate, in rate, x of rate, scan rate. So these are configured for the entire model. The main benefit is, as I mentioned, it cannot be changed during the simulation. And the main thing is we can use this as a in multiple locations, which can be shared. Like say the bus width is constant in the entire simulation, entire design. We can say the bus width is 32 bits. Then it can be used in any internal logic saying, okay, this is the bus width, which is configured by the user. So that kind of a parameter configuration is necessary for any design. So it will be helpful for someone to later change the configuration. They can just select this value and then change it as 32 to 64. They don't have to worry about changing in every other logic. So that is one thing. And they have a function called variable list, which can be selected again in the model list, variable list. We have one here. So it defines the variables such as local or global. So with this, we can define the initial value, and the internal logic can utilize this one and update its value during the simulation. So these will be used for accumulating the statistics throughout the while executing the model. So, and then one more thing is, next is the architecture setup. So, sorry. In this model, we don't have to worry about the architecture setup because these are basic blocks. So, and we can obtain the statistics using another block called resource statistics. So, this is as per the wish customer. If customer wants to obtain the statistics, they can use this resource statistics block. So, where to get this architecture setup? So in this library section under the hardware setup, we can select the architecture setup block and drag and drop it. And we don't have to configure anything. It will it is designed to observe the statistics from all the blocks automatically. It will just observe the statistics from whatever the block that are capable of providing the statistics. So when user wants to try a complex design or some circular design, user have to use the architecture setup to observe the statistics. And one more thing is the power table. So with power table, we can again select the from this library, we have power table under power. User can drag and drop it, but user have to configure it in detail. They can, for example, initial stage, if they don't have proper values, they can just use this entire line and they can define the just value. By default here we say 70 for standby state, 300 for active state, and for weight and idle is 0.0. And what is the state change, like final, like a state machine? What is this change in state? And what is the time between T on and T off? What is the frequency? What is the voltage? So user can configure it in detail, or at the initial stage, if they don't have proper specifications, they can just use default values to try some to explore the power consumption, power analysis. They can also use some like in a DVFS case, like based on the frequency, the power can change. For those things, the user can try some the variable configuration, like dynamic changes in the power consumptions. So we support these features using the power table. So these two are like for complex circuits, and it is the power table is according to the user. If user wants to use this, they can add it. Otherwise, they can ignore that. But digital simulator is very important for all the design. So along with this, let me explain the simulator types. And okay, one more thing before the simulator is the traffic. So for any design, we wish to send some inputs to the design and analyze the impact of the design. So for that, we use a block called traffic, which can be observed from the traffic library section traffic. We can use this. The main thing is, as I mentioned, it can be used to say emulate any signal or any data. So with how we are emulating, like how we are giving how to characterize the signal and how to apply the values, for those we use the data structure. So with this traffic block, we can determine the characteristics of the signal, like what is the time it's supposed to start, what is the time interval between each two signal, like consecutive signals, whether it is like these are time distributions. So whether it is a single event, which means it sends a single packet that happens in a single time in the simulation. Fixed values, which means a proper periodic interval of value one. So if value one say 1 nanosecond, every 1 nanosecond the packet will be generated. And similarly, we have uniform distribution, exponential distribution, and normal distribution. So this determines the characteristics of the packet or a signal, how it can be sent out. So the data structure, this defines what kind of information is there in the data structure. So in this one, we can see it defines, says we have different structures, like we have different types of data structures. The basic one is called header, which have minimum fields. Like if I run this, let me do a listen to code in the output of the traffic. So if I run this, okay, I'll stop it. Okay, sorry. For 1 minus 9. Sorry, I think this is sufficient. So at 0.0 itself, this traffic block created a packet for single event. So with this listen to block, we can see this header basic data structure contain what is the block name, what is the delta which can be used by the user at just default 0.0, and the data structure name, and this ID which says if I generated second packet, it must have said 2. So 1, 2, 3, those ID for each packet will be there, and index and time. Time is the time at which it is generated. So in this one, we can see the index and delta is a just an added field. It describes it describes about the packet or a signal. So in this case it is 0.0. So the traffic block doesn't provide any detailed information in terms of how the data is or how the signal is. For that, we use expression list or any other blocks like a script block to model that signal. So this traffic block provides the base data structure and what is the timing characteristics of this. So this is more important for every design, so that we can analyze the functionality of each design that we implemented. Is there any doubt or questions? Right. Okay. So this is the types of simulators that we have in VisualSim. So the one I just showed you is the digital simulator, which is used in most of the digital logic designs. We can use this digital simulator, which is a discrete event simulator. There are two other simulators which are untimed simulator, which is used in synchronous data flow devices applications. So it uses like multiple components, uses a synchronized data flow transfers with a centralized clock. Example like a DSP or image processing. For those applications, this untimed digital simulator can be used. And we have another one called continuous time, which can be used in analog simulations like communication devices or control system designs. So when we design those logics, we can use this continuous time. Do we have any question so far?
Yeah, about the power tables, is it also used with differential equation?
Which one? You mean the power?
Uh, when user want to use differential equation to for adapt the power estimation, then the user can write the equation to into the power table.
Okay.
Yeah, so is it possible to use it?
Yeah, you mean this one? Oh.
Yeah.
Yeah, user can try this. User can define according to the specification and link this value to this configuration. Like here, the cycle time is used here. So similarly, they can define the any formula, any expressions, and they can use it in the for specific block or everything. So it is the user's choice.
Okay. Yeah.
Is that clear?
Yeah. Thank you for your explanation.
Sure. Okay. So next, we will talk about the modeling methodology that we follow in VisualSim. So with VisualSim, or in any other situations, first we have to define the specification of any device. Or say, if we are designing any custom chip, then we have to define the specifications. Like in terms of, we can use an Excel sheet or any other form to define what are the specifications, what are the requirements of the device, how it's supposed to be, what are the components it must have, and what's the idea behind the design. So based on the number of components, what are the components we have, we list out the specifications saying, okay, this is the traffic, this is the input, let's say this is the cache we need to be associative cache, or we need 32 KB cache. The bus with we have to use a bus between L2 and DRAM, which must be with the 64-bit width, and we must have a scheduler to select the resources. So we have to define the components that are needed, and we have to define a specification saying what the major idea, like the initial specification. So this is what we are going to try. So with this, we define the list of components, and we can select those components in VisualSim. So user can just drag and drop the available, like readily available libraries. They can drag and drop it, and they can configure it. So the initial specification can be used for configuring these devices. Let's say the speed, width of the device, what is the traffic profile will be, what kind of data will be transferred between the devices, what kind of algorithm, like we have, like in terms of we implemented specific algorithms by default. Like we have in buses, we can have round robin or first come first serve, or we also provide some option to design the custom algorithms. So user have to configure those information and assemble those library blocks, like enabling the connection between L1 and L2 cache, or like for input queue to output queue. So they have to configure it and assemble the library blocks, and they can run the simulations. So once the simulation is completed, they can analyze it using a wide variety of resources we have, like the plots, text displays, histogram plots, and the resource statistics. So user can define according to their expectation. Like it is not like it is better to view in a different angle. Like I just want to observe these two particular ports. User can do such things, and they can analyze the results based on the expectation. Like if something is not it seems correct, but the performance is not as expected, so it is providing a loss, or it is more than the expected performance or less than the expected performance. They can analyze it. They in that case, they want to experiment this. In every design, the regression analysis is important stuff. So they can experiment with different parameter configuration. So they try different speed, different bus width, or different number of channels. So with this type of experiments, they can find different values in terms of results. They can find with this method they can find the optimal configuration. So based on the like with this multiple analysis, they can find the optimal configuration, which can be, say, like a final decision is hired, we can use this configuration for implementation. So this also obviously we know the simulation provides a lot of reduction in time. So this methodology is what we follow in VisualSim. Okay, is there any question so far?
Nothing.
Okay. Okay, so let me open few models in VisualSim. Okay, first we will see how to analyze this model. So this is a flow control model, which is a credit-based flow control. We have an ingress queue channels and egress queue channels. We have two flows. Each has an ingress queue with a smart controller, and we have an egress queue. So in this configuration, we are enabling the flow control between the egress queue and the egress queues. So what is happening is, based on the credit availability in the ingress queue are just sending the packet out. The smart controller observe the credits in the egress queue and allocate or issue the packets according to it. So let's first examine the parameter configuration. In this one, we can see the simulation time is running for 0.1 millisecond, and the ingress size, which is the number of channels in the ingress queue. So it says 3 channels in the ingress queue in both of them, and threshold is 5, which is used internally to select the um, to establish the kind of threshold, and x of threshold is used here, and the output rate, which is selection yeah. Okay, so similarly the queue depth defines the depth of the queue, like what is the size of the buffer or queue, and x of rate is the x of queue, the rate at which the x of was sampled or sent out, and scan rate, which is used for scanning the queue in the smart controller. So these are the parameter configuration. So if user want to try some different configuration, say if user want to change the threshold or change the scan rate or the output rate, they can just try in the top level. And the main thing is these are used in multiple locations. The user don't have to worry about changing in different locations. So this is traffic. So this traffic is using the same header basic data structure, but with a in rate. So which is we have seen, sorry, the in rate is 20 megahertz. So for the traffic one is sending the packet at every 20 like in the rate of 20 megahertz, and traffic two is doing the same. So with a fixed mean value, the traffics are getting generated. And in expression list, we are modeling the signal or data, which just saying like what is the size of the packet or data, and setting the priority for it, and what is the queue. In this one, the queue defines the which channel it's supposed to go, and the channel name, and the delta value, which is the user wishes, like user using this delta value to define some value to this particular packet or data. So this traffic is modeled here and sent to appropriate channel. The queue is configured accordingly, like queue number field says queue, which is defined in here, and priority is also defined here. So based on this, the queue accumulate the packet to particular queue. Similarly, we have this the flow second queue have accumulate that, and the smart controller is going to scan the particular queue. So the smart controller for the top one is going to scan this queue and also going to check the credit available in the egress queue. So based on the availability, this is going to send out the packet through this queue to this intermediate channel. So in this one, it is also having an X on X off based flow control. So it will send out the packet, issue, like trigger the packet from this queue to this queue based on the particular time traffic configured here. So every x of rate, half of the x of rate. So here we have x of rate of 610 megahertz. So for every 305 megahertz rate during with that speed, it is sending the packet, like passing the packet from within this intermediate queue. So in the egress queue we can see everything, like both the packets, like we have two flows, each are getting accumulated here. But say like if there is no smart a flow control mechanism, there's a high chance the packet can be dropped, so it can be discarded. So we have to enable the flow control. So this implements a credit based flow control, which is availability in the egress queue. So let me run this model. So we can see we have a different plots and text displays which are defined by the user at the time of design. So in this one, we can see this is latency plot, which can be observed here. So this time data plotter saying what is the latency of each packet reaching at the end of the output queue. So we have two flows and each of them is passing to the output queue based on the credit availability and the traffic rate, the X on X of traffic, this channel. So we can see the time taken by the each packet. We can even select the particular region and select the to observe the particular value. We can like say now it is in points. We can say dots, which says okay exactly what is the value of the packet that is came out at this time. So at 1.794.45, it is came out with a maximum latency of 1.6 e power minus 5. So this defines the latency observed at the end of the egress queue. Similarly, we have some other plots. We have histogram plots. This says what is the histogram plots of the latency. So we can see there are makes maximum of minimum latency is achieved. So we can see this region is what the maximum packets are passed out the queue with let's say 1.5 e power minus 7. So we can see even there are packets at the end of this, but those are very low flow, very few. So some packets are coming out with 8.25 e power minus 5, but those are very few, like only one packet came out. So we can observe, if user wish to observe the histogram plot, like how many packets are using this particular latency level, they can observe this. And similarly, we have buffer occupancies in each of them. Let me explain the statistics. So this text display shows this is just a data structure, like what is the output packet looks like. So we created a data structure with simple header, like say we said header will have some 5 fields, but it during this like passing through the design, we have added a lot of feature, like a lot of characteristic to that particular signal or data. So we can see we added size and priority, which are added in the expression list here. And we also added a functionality called time array and trace array. So with this, user can observe what is the path this particular packet took. So this particular packet is entered the ingress queue 2, which is this one, and passed out of came out and joined an x on 2, x on out, x of 2, x on in, and then egress 1, egress 1. So this shows this is not this is a simple example because we have limited like very few library blocks. But in case if the design is very complex, the user can use this information to see what route the packet take. So this will be very helpful for someone to debug or identify the packet flow. So this is the data structure again and the statistics. So this is the statistics generated by the resource statistics block. We can see that it is generating, we have configured it to observe the statistics for ingress size and sorry, ingress 1 and ingress 2. So these three blocks are observed by this resource statistics block. We can see the number of packets entered and exited in each packet. Like this one is for egress queue. So 1094 packet have entered, but exited is 1090 for this 100 millisecond, like 100 microsecond. And we can see the utilization of this particular block. So this egress queue is utilized, this channel, we can say, this egress channel is utilized for 94% of the entire simulation. Similarly, we can see for different blocks. If this is one, we have multiple of them. Yeah, this is for ingress 1 and for ingress 2. So also along with that, the designer has added this particular statistics called input throughput and output throughput. So input throughput is how much bytes that is processed by the input queue, that are ingress queue. So ingress 1 and similarly how much packet is processed at the output. So we have three channels, right? So we have in particular ingress 1, we have three channels. So channel 1, channel 2, channel 3, these are the packets that are processed and sent out through the channel. At the output of this egress queue, these are the throughputs observed. So these are beneficial for someone who wish to understand, like observe the, like analyze the throughput of the input and output channel. So similarly, we can, so these are the statistics generated for this particular design. So with this, user can, let's say, now the latency is very high here. I want to somehow reduce it. Maybe in this design, user can try to increase the queue depth. So in this one, let's say it is 100. User can try to increase the packet for 1000, or let's say in a specific place. These are they can try some experiments and they can find out whether it is providing any optimal solution or not. So this is one model. Let me explain a different model called software task. I will explain, like if you wish to observe this model, I will provide the location after this meeting. So let's say let's take this example. So this is a model that design the software task flow using the system resources. So we have two application flows, application 1 and application 2, which uses this as a task flow. So we can see first it is going to access the IO, then it is going to pass through the bus 1 and then the CPU 1 and then bus 1 again and then DSP and bus 2 and IO. We define this is the flow this application 1 is supposed to take. So we design this flow and similarly we design the application 2. So this is going to trigger these system resources. We have a system, the system resources internally. So this will trigger the system resources and perform the task with a specified time delay. So we have defined the time delay. So we can see the application 1. This parameter says what is the time for each resources that pass through this application. So let's say IO is going to take 14 millisecond or something. CP1 will take 220 cycles and DSP will take 100 cycles and IO will take 2 cycles. These are not for buses, for the resources in the application 1. Similarly, we have defined for application 2. So those are configured here. So the IO uses the application 1 times 0 within that array and application time 1. Similarly for everything. So these are configured in that way, and this will trigger these resources to perform the task according to this time. So we are sending that time, and similarly we are saying this is the resource destination. So each of them is constructed using the system resource. The system resource is very helpful in terms of designing a system level model. So we don't have, in this case, we don't have to worry about the internal configuration in detail, but at system level, it is going to perform the task as expected. Like if in this one, it is a default case, we can configure the time delay according to the speed. So it can also be designed. So let me, we have also the power table. Let me show an example one again. So in this one, we have CPU1, CPU2, and DSP and bus 1 and bus 2. We have defined the states here. So CPU1 has the values of that, and what is the time, the power values for wait and idle, what is the standby, what is the stage, and what is the frequency. So these values, according to this, let me. So these system resources are sends the signal whenever it is getting activated. So whenever there is a task being processed, this will send the signal to power table, and this will analyze, like observe the power consumptions of each of them. So let me run the model. So in this one, we can see the task latency first. So which is this is the task latency for application 2. So we can see the each packet generated by this application 2 traffic is processed by these system resources, and we can find the latency of each of them. It is not like constant. So we have each packet is taking different routes. So in this case, we can see the bus one is not just about going to bus one. It can take bus one, bridge, bus two to obtain the data from resources from this CPU2. So similarly, we have defined the flows and the latency for it. We can see the time taken for each task. And let me open the histogram plotter. So this in this model, the designer used this histogram plotter to observe the latency of each task. Okay, so let's say in this one we have application one processing, application two processing, which are the red and light blue. So we can see these two things. The application one processing has less latency compared to the application two, but this says what is the latency level. So application 2 was using 0.8 region for the 60 or 70 number of packets uses the 8.8 latency. So similarly, we can see the application 1 transfer and application 2 transfer. So we can see the application 2 transfer has higher latency, higher number of packets using this large latency values, because this is using bus. In this one, we can see it is just using bus 1, but in this case we can see bus 1, bridge, bus 2, and then it is going to DSP. So CPU2, bus 2, bridge, bus 1. So it is defined accordingly. We can see the latency reflection on that. So this application 1 total time and application 2 total time, we can observe that the higher latency is observed in application 2, around like 1.5, greater than 1.5 microsecond. Those have large number of latent packets using this one above latencies above 1.5 microseconds. So this is one way of analyzing the model. It is not necessary to use the histogram always, but it is user's choice. But the main idea is to observe the latency and power of this design. So we found this. The next one is the statistics. Okay, so this is the statistics observed using this the same time taken by each task. So this is the reflection of the histogram plot. So this says for each packet, what is the time consumption, like what is the time delay for processing and queuing. So this is for each resources. So for IO, CPU1, CPU2, and again IO. So what is the time it take? And similarly, we are using we are observing the transfer time, which are the bus interconnect device time. So for bus 1, bus 2, and bridges. So for each packet, it is generating this the delay information, and the same is observed in the histogram now. So the actual statistics generated by the resource statistics blocks is this. We can see the similar thing, like as we observed the statistics in the flow control model, we can see the statistics of like for each packet. Like for a bridge, it was using the number of packets is entered, like 707 packet has been processed through bridge, and the utilization is 49%. So 49% of the time during the simulation, the task was active in this bridge. Similarly, we can observe the statistic for bus 2, bus 1, CPU2, CPU1, and all. So again, as I mentioned earlier, user can try different configurations, like For now, user can try. These are the power states, like power active, power standby. These are defined by default. So user can change the value to see, okay, whether it is giving an optimal config, optimal results, whether it is improving the performance or not. User can try this on, or user can add some other resources like, okay, I have changed the design. Now let me add another CPU2 in the between bus 1 and DSP. So I will, user can add this system mapper. User can utilize this one, or they can replicate the same kind of information that will utilize the CPU2 here, and then it will go through bus 1 or bus 2 and then to DSP. They can change this configuration in terms of architecture level or in terms of parameter level, like what is the latency, what are the power state values, like let me run the simulation for longer time, like 200 microseconds. So they can try these. So this is one way of observing, like defining the model, defining the algorithm or design in a task flow level. Is there any doubt so far?
How to put the software task in to sub design model? For example, the task CPU1 mapping to CPU1 block.
You mean how it is mapping to this task 2 is mapping to CPU1, right?
Yeah, that's right.
So we have a functionality called mapper and system resource. So this mapper is configured with this device name, target resources device name. So this enables a virtual communication. So we have defined the name as bus1. So
okay.
this sends a signal to this CPU and it will process accordingly. Like it will have a detailed information saying, like as I mentioned, it will say the device name and the device time. So those are sent to the system resource which is inside this. Which is the device name is again a parameter CPU. So it will utilize those information and process it. So it has internal queuing. Like if say both are sending the same information. Like this one is using CPU1. Let's say if I put another CPU in between CPU2, say these are both are using CPU2 now. So this has to wait. Like the scheduling and ordering will be there. So there is an internal queue called, now it has 30 buffer size, and it will allocably enqueue them and process it sequentially and then send it back to the appropriate flow. So those can be handled this way.
Okay, I can fully understand it.
Okay. So this is one model that I want to share, and there is another model I can show is power performance model. So this is a design to analyze the power consumption of a multimedia system. So in this one, we have internal functionality such as the ARM processor. We have a two-core ARM processor with cache, XA bus, and the SRAM, boot RAM, and we have SDRAM here. And also we have a hardware accelerator which is defined using this system resource. So again, the main purpose of this model is to analyze the power consumptions of each devices. Like they have defined, okay, what are the devices that they are going to analyze. So let me explain the flow first. So we have a traffic that generate the instructions for that needs to be processed. It is going to select the flow, whether it is going to select this mapper which uses the ARM directly, or it is going to process like a digital signal processing. This one is going to process first. It is going to process, let's say, the image processing stuff. So it is going to observe the value from sensor, read the frame, decode the frame, and process it, and then convert the frame and display it. So this is the sequence of like a similar to software application, the earlier model that we just saw. It is defining the flow of action, like flow of execution. So it will send it like similarly. If we go into this, you can see the dynamic mapper that is mapping to the ARM processor, and it says the time, everything. What is the task time, what is the priority, and what is the instruction that we are going to process. All informations will be sent to the processor, and it will be processed. So if I run this, before that, if we check the top level parameters, we can see we are defining board name, what is the speed of AXI, and what is the burst name, and select the partitioning. So this is a top level parameter, but internally we have a hierarchical parameters. So let's say the ARM subsystem have internal parameters. So it's a second level parameter configuration. So this will be specifically for the ARM subsystem. So it cannot be used by the any other device outside of this particular block. So we can see here, which is the processor speed is 200 megahertz, and cache speed, size of the cache, and in terms of high cache, D cache size, and what is the ROM size, what is the AXI speed internal to the ARM subsystem, and what is the transaction size. So user can configure it, and if after every run, they can easily change some values to try different experiments. So also we have power table here. You can see this is a detailed configuration because we have a lot of library blocks with a complex structure. We can see within the streaming board, which is this particular ARM subsystem, which is the board name. So within the streaming board, we have ARM and another processor called Move and cache, hardware accelerators, HP bus, flash, ST-ROMs. So we have configured the values for all of them. So for this particular one, we have standby of 75 watts, and we for this one we use 25 and 50 150. So it is according to the specification. So user configure this, and the signals according to the signals sent by the each devices, the power table consumes like analyze the power. So let me run this model. Also we can see there are some blocks according to the architecture. So we can see this there's this instruction set block which can be used for when we use the block called processor. So this is a hybrid processor in VisualSim. When we use that, we have to use the instruction set to say that it is the one providing the detailed information about the ISA. What is the instruction name? What is the instruction cycle? How much cycle it will take? What is the type of instruction? Which execution unit it can execute? So those will be here available here. So it is according to the design. So it is not necessary for in all the cases for the processor based system. This instruction set can be used. But this architecture setup, digital simulator, variablist will be there in almost all the basic models also. So now the simulation is completed. You can see the first power consumption. Like we have designed to analyze the power specifically. So we have used an histogram to see how much power is accumulated in each device. So this one, it is for three. It is designed for three of them: ARM, which is ARM processor, cache, hardware engine, and DRAM. So we can see the DRAM is the one consuming more power. So this is the percentage. We can see like almost like 12% of the power is consumed in DRAM, and almost like 7 or 8% is consumed in ARM. Similarly, in terms of usage, we can see in terms of watts. This is in terms of percentage. We can see in terms of watts, ARM is using around 2 milliwatt and DRAM is using around 3 milliwatt. So along with that, we have designed the activity diagram, which says like we have for all the devices in this system, in this design, we can see what is the activity. Like this one is corresponding to DRAM, which says refresh. So how many times the refresh is happening at what interval, at particular at what time the interval refresh is happening. So we can observe the activity of DRAM, and also this correspond to the register read write and integer one execution. So according to the traffic we design, we can see only it is not accessing the cache. For in this case, it is processing the. It seems the register var contains all the information, and the integer one is alone being processed. And due to the refresh, the DRAM consuming a lot of power. So this is the activity diagram. We can say, okay, what kind of devices are active, what kind of devices cost the power consumption. we can observe and analyze these things. And we have used another is so time data. But what is the time in terms of, and this is the current. The thing, the current is constant in all during the entire execution, and the instantaneous power. This is the power, instantaneous power observed in the execution, like from 0 to 2 for a 20 millisecond. We can see the instantaneous power of each task. For this particular task, it was taking around 1.45 milliwatt, and for the remaining it was reduced and it was remain constant. So we can observe the instantaneous power for each task throughout the execution. And similarly, we can, this is the average power plot during the simulation. This power, what is the average power consumed by the name is wrong, I believe. So this is the average power consumption of this entire RAM. So again, as I mentioned in the previous models, user can try some different experiments. They can try different configurations like changes in the access speed or the increasing the call rate, and also in terms of specific subsystems. Like in this case, we can change the cache speed, cache size, or the width of the transaction. What is the transaction bytes? User can try different configurations and they can observe the results. Like they can fine tune the configuration to see the optimal results. So this is one model that I want to explain. Is there any doubts in this one?
I think I need to review this demo after this meeting, and
Okay,
yeah,
sure.
yeah, I will try it and let let you know what I need to more information or your explanation.
Sure, okay. Okay then. Okay, then I will show the second model, the last model that I want to explain. Then we can discuss in detail if you have any questions in this one.
Okay.
Another model. Okay, yeah. Do you have any question?
Nothing. Yeah, yeah. Please go. Keep going.
Okay. Okay, so I'm opening an automotive networking based model now. So in this model, it is we are going to use the gateway to enable the communication between the CAN bus and the TSN switches. So let me explain that.
Are there any algorithm model or libraries?
Which one?
Uh, are there any algorithm model or libraries?
IO design. Is that correct? Which model? Like, can you say it again?
Or for example, uh, uh, FFT filter or some something is or HPC application or etc.
You mean the application-based modeling? Is that correct? Can you like maybe can you type it in the chat window? I couldn't. There is some issue with my micro speaker. Yes.
Yeah. Where if I wanted to run the HPC application, then how the user can uh, run it with VisualSim simulation?
Okay, like can you mention the application in the chat window?
Yeah. Yeah. Some user would like to run some specific application in C level. Then how they can um,
Okay,
import
can you
the
can you
library?
give me the any example like I think you mentioned specific application, right?
Yeah, yeah.
Okay, so for example, let's say if user wants to try processor based application, like running some specific workload, we have a model right there. Do
Mhm.
you have any specific example in your mind?
Uh-huh. Okay, that's okay. Uh, sorry. I
Yeah.
think yeah. I think you should provide some example
Okay,
yeah to me.
so this is actually like based on an automotive application. This is a design on analyzing how the transaction and the latency impact and communicate, like enabling the communication between the CAN and the TSN switches. You can see the if I run this, like the main configuration is the MTU time, the maximum transfer unit time. So if I run this, we can, yeah. So this is an observation in the gateway. So this block is saying, okay, what's the latency took in each path? So channel one, this is between the higher latency is the one is channel 13 to channel 22, which is you can see from, yeah, this is the channel 13 and this is the channel 23. So between these two workloads, we can find a higher latency transactions. So all of them that are transferred between this uh, workload prio to the TSN switch contains a high latency one. And the channel 1 to channel 22, which is this one, where this CAN bus, this CAN node 2 is transferring data, the transaction between this node and this gateway TSN switch to the endpoint has a varying latencies. You can see the blue dots and lines. And similarly, we can use the channel 1 to channel 2, which is between CAN node 2 and CAN node 9. So this shows the latency of each task that is transferred through this gateway. And you can see the end-to-end latency, which is observed in this one. So at the endpoint, we are calculating the end-to-end latency that is transferred from this point to this, like whatever the packet generator from this from CAN node 2 or workload 1, what is the end-to-end latency of this packet? So we are observing, we can observe that end-to-end latency here. Though, so this is designed specifically to observe the latency at this point. Similarly, we can see the throughput at the endpoint. Similarly, similar to latency, we are observing throughput obtained at this endpoint when the packet reaches through this TSN switch 2 at the end. We can see the what is the throughput of the packet. And with respect to statistics, you can see what is the number of total bytes processed by this switch 2 and Ethernet 6. So switch 2 in the sense, this is switch 1 and this is switch 2. So what is the total bytes it took, and what is the is there any number of, is there any rejected packets, or in terms of latency, you can see what is the minimum latency, the maximum it took, and the mean latency, the average one. Similarly, for the throughput, you can see minimum, maximum, and average throughput. So in this, we can see this particular flow doesn't have much of an impact. So it was just using 160 bytes. But This one we can see we have this flow uses 97280 bytes, and the latency and throughput we can see there's a difference. So this is the throughput between this switch 2 and switch 1. This is about the gateway, like we can observe the channel, what is the total bytes processed by the each channel, like source is channel 1 and channel 2. Between these two channels we can see 1440 bytes is transferred. Similarly for all others. And what is the buffer usage of each of them? So what is the each buffer usage in the input, that is channel 1 and channel 13 and channel 23, and the output of channel 2 and channel 22. So in this one it is maximum buffer occupancy is 1. And other than that, user try to observe this data structure at the endpoint. So user just whatever the packet that are getting completed, user can observe that. So at this time we are getting a packet output, and these are the fields that describe the packet. What kind of information, like what is the checksum value, what is the connection number that it was went through, an acknowledgement number, and some other flags that describes this, like header and additional information for the particular packet. And it will also contain the trace array and through time array. So as I mentioned, it will be helpful for user to observe what direction the packet was traversed through, and it will be easy for debugging and changing the flows. So these are the models that I want to explain. And you can see if I say let me increase the I'm not entirely okay. It says 101512. I will say 2048. We can see the increases in latency. Like earlier, it was less than 1 e per minus 5. Now, due to the changes in bytes, like the data transfer between the gateway, it increased. Like now, it is we can see the changes in the latency and throughput. So it is according to the, if user wants to increase the throughput because it is like increase the byte size, it is necessary. The payload is increased. Then there is an increase in latency. Then user can try different configuration, like improving the speed of gateway or TSN switch. They can optimize it. So these are the methodology that we follow. As I mentioned, we know how to design the specification. Like user will have the specification saying I will have two canvas and each will be connected to specific sensors or actuators, and I will have TSN switch that will be connected to specific the central systems or some processing units, and I have to enable the communication between the sensors and communicate the central devices through we need a communication, so we tried a gateway. So this is a design in an initial design that they have in mind. So after assembling this and making the connection, user can observe what is the impact of the design, whether that is providing a proper better performance or not. Then user can try some different configuration to improve the performance, or to let's say just try some experiment, like let me add another TSN switch or a sensor, so how it impacts the system. So user can try different configuration in this manner. So is there any doubts or questions?
Nothing. Yeah.
Okay. So I have defined like the main idea is to show these four models, and if you have any specific request or question in mind, I can try to satisfy explain those. From application perspective, we have a lot of demos. Even in this one, you can see the application based on automotive, antenna, and networking, and system architecture, signal processing. So user can select any model within that, and they can experiment or observe the results. So even we have memories like specific to memory and failure analysis, power consumptions, everything. So if I go to the hall, in this folder has some lot of detailed uh, architecture based models. Like we have mixed SoCs, GPU, ARM based models, and RISC-Vs, Tilelink. So user can try these things also. Do you have any question or?
Is there also AutoSAR hard?
Yeah, we have an AutoSolve model.
Ah,
So it is designed for a long time ago, but this is an example. Okay, so in this one, we can see the sensor. The nodes are there, which are connect through, which are enabling the transactions. Okay, so if we, based on this results, we can see EC1 and EC2. So it's just observing ECU hardware. Okay.
okay. The examples or included the VisualSim.
Okay.
Yeah. When or the examples included in the VisualSim library.
Yeah, these models will be there in VisualSim. Whenever the user install the tool, these will be there.
Okay, then yeah, I will try it. I will try it.
Sure.
Yeah.
Okay,
Yeah.
so do
Okay,
based
I'm
on
not
this
having.
presentation, yeah,
Sorry.
sorry. Like based on the presentation that we saw, do you have any specific questions?
No. Yeah, I'm not having any questions.
Okay, okay. So, like I will share this presentation and the model location that I presented in this training through mail. If you have
Okay.
any question, we can. I will further clarify that.
Okay, that's great.
Okay. Okay.
Okay.
Yeah.
Thank you for your training session, and yeah, I'm
Sure. No
glad
problem.
to I'm glad to run your yeah session.
Sure. No problem.
Okay.
Okay. So we will have a meeting. The second part will be on Thursday. So I will. We will see you at that time then. Okay.
Yeah.
Nice meeting you.
Yeah. I'll
Bye.
see you again. Yeah. Have a good time.